Hi everyone, welcome back. Let's proceed with the final presentation in today's session, which is, as you can see on your screen, methods of generating Comtrade files using EMTP for testing traveling wave relays. Our presenter is Toby Russell. He's a graduate student at Louisiana Tech University. His research focuses on traveling wave relays, and he's working under supervision of Drs. Prashanna, Bhattarai, and Dr. Mikey Cox from Entergy. We also have Thomas Field from Entergy. I believe Thomas is going to start the presentation, and then Toby is going to take over. So I let you guys proceed the way you want it to go.
Good morning. My name is Tom Field, and I run the university research projects at Entergy. One of the projects we funded this year is the simulation of the SEL-T400L traveling wave relay in EMTP RV. Dr. Milton Quinteros, who is the project lead at Entergy, was going to discuss the project further today, but he is not able to make it. The relay model will be used in simulations by Louisiana Tech for a pilot location we have selected for the new relay. Because it is a new technology, there were some technical challenges not originally anticipated. The presentation today will cover one of the challenges that we thought might be helpful to other EMTP RV users that will be working with the new relays in the future. This slide shows the team members on the project at both Entergy and Louisiana Tech. I'll turn it over now to Dr. Prashanna, Bhattarai, who is the principal investigator on the project at Louisiana Tech.
Thank you, Mr. Field. This is Prashanna Bhattarai from Louisiana Tech University. Before we get into the details of the presentation, I would like to give some background. As Mr. Tom Field pointed out earlier, Entergy is planning to install the traveling wave relays in their transmission system. Before installing it system-wide, they are first doing a pilot study, and as a part of that pilot study, they are funding Louisiana Tech to develop the computer model of the relay to run simulations before the actual pilot installation, so that they can determine any unforeseen issues. So that brings us to our project summary, which is Louisiana Tech is developing a model of traveling wave relay using EMTP that can closely mimic the operation of the SEL-T400L relay. When we started the project, we only planned to develop the computer model of the relay. However, during the course of the project, SEL provided two SEL-T400 relays to Louisiana Tech. Now, at Louisiana Tech, we do not have any relay test sets. Therefore, we are relying solely on the EMTP generated Comtrade file playback for testing the relays. As we started working on this in more detail, we encountered many unforeseen issues, and so the issues were arising due to things like currently a standardized procedure for testing SEL-T400 relay using Comtrade file playback from EMTP does not exist. So LA Tech is working with PowerSys and SEL to standardize the Comtrade file playback process. Furthermore, we are also testing the beta version of a Comtrade file generator add-on to the EMTP library. So just to be clear, although our main project goal is the development of the relay model, this presentation, however, is not focused on the relay model development. Rather, this is focused on the testing. Or the testing procedure. So now let me hand it over to our graduate student, Mr. Toby Russell, who is the main person working on this topic.
Thank you, Mr. Field and Dr. Bhattarai. My name is Toby Russell, and I'm a graduate student at Louisiana Tech, focusing in power systems. Thank you to everyone watching, and I hope you enjoy this presentation. This presentation will discuss two methods of generating Comtrade files with EMTP and how to use them to test traveling wave-based functions on SEL-T400L relays. A brief demonstration video of this process will follow. Traveling wave relay testing can be performed with modified current and voltage injection methods, where capacitive discharges are superimposed on steady-state current and voltage signals to mimic traveling waves. The SEL-T400L can be tested using digitized analog signals applied to the relay. Comtrade files used to test relays can be generated with two different methods, and this presentation will focus on how to generate and play back Comtrade wave shapes that were generated with both methods. I will discuss some of the pros and cons of each, as well as any pitfalls that may be encountered. To begin, I will provide a brief background on traveling waves. Next, I will discuss some popular methods of testing traveling wave-based protection elements. Then, I will provide an overview of event playback testing, including some of the specific file requirements. I will discuss two methods that can be used for generating the Comtrade files, outlining the important features of each. Finally, I will summarize the procedure for loading the Comtrade files on the relay and provide a short demonstration video of the entire process. The main problem this presentation addresses is that generating the high-frequency transient data associated with traveling waves can be difficult, and there are a lot of unknown factors that can affect the operation of a power system at high frequencies. Testing traveling wave-based protection functions can be completed with modified voltage and current injection methods, but the main problem is that most test sets on the market today cannot provide a true representation of the high-frequency transient data due to limited bandwidth. This presentation will focus on one solution to this problem by providing an accurate, high-frequency representation of power system transients using EMTP-generated Comtrade files for testing traveling wave-based protection schemes. It's important to note that the Comtrade files will not be loaded directly on the relay, but they must be converted to playback files first, which are then loaded on the relay. For a fault on an overhead transmission line, traveling waves are launched outward from the fault in opposite directions, and they generate reflections when discontinuities are encountered. These waves propagate down the lines at almost 300,000 kilometers per second, or light speed. If the line length and exact velocity of propagation are known, the arrival times of the traveling waves can be used to determine an exact fault location. These traveling waves have a very fast rise time, usually on the order of a couple of microseconds, though dispersion effects can cause the waves to be slightly stretched. The initial slope of the first traveling wave is used to determine the arrival time of the traveling wave and must be accurately represented for testing. The traveling waves contain high-frequency data, and to study their effects, the transient behavior of the power system must be considered. There are three main ways to test traveling wave relays. First, by coupling some precisely timed capacitive discharges with a secondary injection test set to generate synthetic analog signals to be applied to the inputs of the relay. This method is mainly used for commissioning testing. Next, using real-time hardware-in-the-loop transient simulators that generate a digital representation of the power system operating in real time. And last, by using an electromagnetic transients program, such as EMTP, to generate an accurate high-frequency simulation data that is played back as a direct digital input to the relays. Secondary injection test sets designed for traveling wave testing create the initial traveling wave per phase and sometimes the first reflection. Capacitive discharges are used to model the steep rise time of a traveling wave's arrival at the relay terminals. These discharges are precisely timed to mimic the arrival of traveling waves. This type of equipment is used for relay commissioning testing in the field. This is basically just testing that the relays are hooked up correctly, working as intended, and running the most up-to-date software. Traveling wave testing with injection test sets can be difficult because they have a limited bandwidth. This method is also limited by the nature and number of capacitors. They can deliver only a limited number of traveling waves, and only no or one reflection can be considered. New to relay testing is the ability to run playback files directly with only a computer in the relays. This allows high-frequency data simulated in the computer or captured from real-time power events in the field to be loaded directly onto the relays, bypassing the need for a high-bandwidth amplifier. This is a great way to test the relay's response to transient events on the power system. Event playback testing allows users to test the relays in the lab by playing back computer files containing accurate high-frequency data of the power system. This data is stored on Comtrade files to be later converted to playback files and loaded on the relay. It provides a very useful tool for testing traveling wave-based protection elements because the data is sampled at frequencies of 1 megahertz or greater. This is mainly used for testing the design and performance of the relays in a lab setting. It's also used for relay modeling as well as research and development. This method provides a complete set of reflections for the relay to consider, and it is used for design and testing traveling wave-based protection schemes. The SEL-T400L and the T401L relays are the only relays on the market with this capability. Due to the high-frequency nature of traveling waves, event playback testing is a very useful feature on traveling wave-based protection relays. Comtrade is short for Common Format for Transient Data Exchange. These files are designed to store data related to transient power system operations. The file type was standardized in 1999 by the IEEE, and there have been several revisions since. For this application, we recommend the 2013 IEEE format. This demonstration will focus on two main types of Comtrade files, the DAT and the CFG files. The CFG files are small and they contain a variety of information about how the data is stored. They're typically around 1 kilobyte and contain things like the sampling rate, signal names, unit, min and max value, and more. The DAT files are much larger and they contain the actual data itself, and they must have the exact same name and file path as the companion CFG file to load properly. As you can see, this is an example of a CFG file. Here are the signal names, the units, scaling factors, power frequency, sampling frequency, and the number of sample points. To test the SEL-T400L relays, there are certain requirements for the computer simulated data files. The files must be IEEE Comtrade format. To test the traveling wave protection schemes, T400L relays can run files with sampling rates up to 5 megahertz. The overall duration of the input file can be between 0.1 and 24 seconds, but the playback files that are actually loaded on the relay are limited to 1.2 seconds of event data. For each relay, the file must contain all 3 current and all 3 voltage waveforms with names that conform to the criteria provided in the SEL-T400L instruction manual. It must have at least 50 milliseconds of pre-fault steady-state voltage and current signals, and the amplitude of the steady-state alpha A voltage must be greater than 5 volts. This demonstration will focus on two methods of generating the Comtrade files. First, the ScopeView method. This method uses the ScopeView signal viewing software included with EMTP. The signals are played in ScopeView, and the Comtrade files are generated by clicking the Export button on the toolbar. The next is the CFG Recorder Method. This method uses an add-on to the EMTP parts library that directly generates the Comtrade files as EMTP simulations are run. The ScopeView method is a simple and straightforward way of generating Comtrade files for playback testing. All of the tools required to generate the Comtrade files with this method are available on the standard EMTP download, and no additional add-ons software is required. The relays require all 6 of the 3-phase secondary signals of the voltage and current transformer to be on one Comtrade file per relay. Be sure to capture the secondary of the current and voltage transformers by scoping the burden, current, and voltage respectively. Also, users must ensure the Save Intermediate Time Points is turned off in EMTP simulation options. This can cause a lot of issues with the EMTP data that will be discussed later in the demonstration video. For the signals captured on the secondary of the voltage and current transformers, I prefer to use simple names like IA, IB, IC, VA, VB, and VC. There is more than one way to change these names, and I have tried multiple methods, including renaming them in the CFG files after they are generated. I have found that the easiest method to change the names is under description in the ScopeView signals window. I put one of the 3-phase voltage and current signals on the first page, one set of, and I put the other set of signals on the second page. What is most convenient about this is that once you have it set up, it stays configured until you close ScopeView. You can run a series of fault cases, and when you play them, the ScopeView signals are already named, configured, and ready to be exported. This is an easy place to make mistakes, so always check for errors here. Here's an example of the selected signals window. As you can see on the left, here are the signals as I've selected them. Under description, I triple-clicked and renamed each, and then I have 6 on the first page and 6 on the second page. This depicts the export button, which is seen at the top of the ScopeView signals window. And when you click that, the export window opens up. Be sure to only save the current page, so the 2 pages correlate to 2 different files. Then always give it a unique name. I typically like to give info about fault type, location, line length, and any other special circumstances to avoid confusion, and so I can go back to the files for reference or future simulations. The export feature generates 1999 standard Comtrade format, but that's okay for this application. Many possible file types can be generated here, but be sure to select the Comtrade for this purpose. However, the .text and .map files can be very useful for different testing applications. The CFG Recorder Method uses EMTP parts library beta add-on to record line data without opening ScopeView. The add-on included 2 devices, the Comtrade Recorder and the Comtrade Replay. The Comtrade Recorder saves line data in real time to a pre-specified file location with a pre-specified file name. The recorder meter must be configured before connecting them to a signal bundle to provide destinations for the signal in the bundle. The Comtrade Replay has the ability to play Comtrade files back in an EMTP. It must be loaded with the CFG and DAT files before it can be connected to the signal bundle to provide sources for the bundle. This can also be a useful tool for downsampling. Blocks that need to sample at a high sample rate can be run at the desired frequency and have the data recorded with the Comtrade Recorder block. Then, in another EMTP file, sampling at a lower rate, the reader block can provide data from the file sampled at a higher rate to be downsampled at a new lower frequency. Figure 8 and 9 at the bottom of the screen show these two meters. As you can see, the recorder meter also is labeled write, and the replay is also labeled read. So writer and recorder are kind of the same thing, and replay and reader are the same thing. And that terminology is used throughout this presentation. Some of the properties I select for the Comtrade recorder. First, the IEEE standard format 2013. I select the ASCII format, and then I've been using the 32-bit precision to capture the data as accurately as possible. There are other settings for this device that will be discussed in the following demonstration video. Here is an example of the Comtrade recorder window. As you can see, I've named the signals the same as before. I've selected maximum and minimum values that are selected specifically for these signals. And under the value measured, I have selected secondary for the secondary of the instrument transformers. Here are the scaling factors, which are calculated from the max and min value and the precision. And if you want to manually overwrite these factors, you can check this box. To use this meter, you need all 6 signals in one bundle. So you have to use the control signal connector and breakouts to accomplish this. I'll generate a 3-pin breakout for each instrument transformer secondary, and then a 6-pin breakout for the device itself. To connect these breakouts, you have to use the control signal connector, and be sure to set up the Comtrade writer before connecting, and use the bundle connector window when connecting it to the 6-pin bundle to make sure all connections are correct. As I discussed earlier, the beta add-on Comtrade recorder and replay meters can be a useful tool for downsampling. To accurately capture the high-frequency data, EMTP line models should be simulated at approximately 4 megahertz. Also, to accurately mimic the SEL-T400L, the signal processing of a computer relay model must be performed at a 1 megahertz sampling rate. This causes a disconnect because there are now 2 separate EMTP files required. If users plan to use only one sample rate, the ScopeView method is the most straightforward way to generate the Comtrade files. But if downsampling is required, the Comtrade files should be generated with the beta add-on blocks. Once the Comtrade files have been generated, it is a relatively straightforward process to load the files on the actual relays. First, the files need to be converted to playback files in SEL's Playback File Conversion utility. This program is used not only to convert the files to another format, but the analog anti-aliasing filter is applied here. Next, open SEL's accelerator program to connect to a relay and open the playback dashboard. In the playback dashboard, users can load files on the relay and initiate test cases. Users must ensure that the mirrored bits and contact output boxes are checked, and a test time should be selected that is 8 to 10 minutes in the future, because once the countdown reaches 2 minutes, no more changes can be made. This is the setup Louisiana Tech uses to run Comtrade files with SEL-T400L relays. The switch in the tabletop server rack communicates with the computer through a gigabit Ethernet connection, and the relays are connected to the switch and each other with fiber optic lines. This is all the equipment required to complete playback testing. This is a short demonstration video that depicts the entire process of generating Comtrade files in EMTP.
Hello, Toby.
Yes, sir.
Sorry to interrupt. If you want, you can also play this video directly from GoToWebinar. We have uploaded it. So in GoToWebinar, under sharing, there will be a show, and under show button there is going to be a drop-down menu where you can select the recording. The name of it is EMTP _conf _v3.
Okay, so I just click that when I'm ready to play.
Yes. Yeah.
Okay, good deal. I will be there in 1 second. Thank you. Please note that for time constraints, section of this recording have been accelerated, and the video does not represent the actual time required to complete this testing procedure. Also, note that this demonstration video covers a lot of details and must proceed at a rapid pace to include all information for describing this process. If you have any questions or want to learn more about the procedure, feel free to contact us at the emails listed below. This is a demonstration of methods for generating Comtrade files in EMTP and loading them on SEL-T400L relays. This is a simple line model with an A to ground fault at 0.1 seconds. We need to scope the secondary of the current and voltage transformers. The Comtrade files need to contain all three phases of the current and voltage data. First, I will configure the simulation settings for this test case. Under Simulation Options, I make sure the step time is 1 microsecond and the total simulation length is 200 milliseconds. Next, I click on the Output tab and make sure the Save Intermediate Time Points box is unchecked. If EMTP saves the intermediate time points, the Comtrade file may include unnecessary information. For this simulation, I expect to see 200,000 sample points for a case with 1 megahertz sampling lasting 200 milliseconds. If intermediate time points are saved, there could be more than the expected number of sample points in the Comtrade file. Also, the extra data points can cause errors in the steady-state frequency calculation and corrupt the pre-fault data needed for the T400L relays to function properly. Next, I will click OK, and I click Run at the top left corner to run the simulation. The runtime of the simulation depends on the step time and the number of devices in the design. Once the simulation is complete, I click View Scopes with ScopeView to view and configure the current and voltage transformer data. Now I want to configure the first Comtrade file. I will need all three phases of VT and CT data, and they need to be renamed IA, IB, IC, and VA, VB, VC. This is done by triple-clicking next to the description of each and typing the updated names. It is easy to make a mistake on this step, so it's important to make sure the desired signals are displayed. Next, I increment the pages and configure the other set of instrument transformer data for the second Comtrade file. After pressing play, the signals will be displayed in the ScopeView window. There should be 2 pages, each with 6 signals. On the first page, click the Export tab at the top of the page. Give the file a unique name so it is identifiable. I typically include fault type, line lengths, and the relay destination. Be sure the file is saved as a .cfg and ensure that the file only includes the current page. Repeat the process for the other page, but be sure to change the relay destination to the right-hand side. After clicking Export, navigate to the folder used to store the Comtrade files. There should be 4 files, 2 for each side, a .cfg and a .dat. The .cfg file contains information about the data, how it is stored, and scaling factors. It also displays the sampling frequency and the number of sample points. The .dat file is much larger and stores the actual data itself. Next, I will need to generate the actual files that are to be loaded on the relays. For this, I will use the SEL file conversion utility. Click the blue load icon on the top left-hand side and select one of the Comtrade files generated in EMTP. Click the gear icon on the top right-hand side of the window and be sure the SEL-T400L analog filter is applied. This is the anti-aliasing filter. Now, holding Control, click and drag the mouse to zoom into the first part of the file. Due to the initial jump from 0 to steady state, we see a small response due to the analog anti-aliasing filter. To remove this point, I grab the orange bar on the left-hand side of the screen and drag it to the right by 1 point. Next, to save the file, click the green save icon on the top left-hand side of the window. The file should be automatically saved in the same place as the parent CFG file and have the same name. Now we need to repeat this process for the files pertaining to the relay on the other side. Now, going back to our folder, it should contain 6 files, 3 for each side. Next, to load the files on the relays, I use Schweitzer's Accelerator program to interface with the relays. In Accelerator, I first connect to one of the relays. Under Communications, at the top of the window, select Parameters. This can also be done with Control-R. I select the left-hand side relay and click OK. The relays have already been loaded with the proper settings for this line model. The connection status of the relay is displayed at the bottom of the window. Each relay has a unique IP address, so we will know what relay we are connected to at all times. Now I want to open the Event Playback dashboard. It can be found under Tools and Event Playback. The connected relay is shown at the top of the window, confirming we are connected to the left-hand side. Now, we need to select the file that is to be loaded on the left-hand side relay. Click the blue file under Test File Management and select the .py that is for the left-hand side. Click OK and click Send to Device. Once the file is loaded on the relay, click the 1 box and be sure the contact output and mirrored bits boxes are checked. Now select the time-based option for the trigger. Notice the clock counting down on the right-hand side of the screen. It is Universal Standard Time. Enter a test time that will provide several minutes to repeat the file loading process on the opposite relay. Now click Initiate Test. There will be a question on the front panel of the T400L. Click Enter on the relay panel to initiate the test. Now I will need to connect to the other relay. I'm on the clock. The test must be initiated for each relay before the countdown clock reaches 2 minutes. Going to Communications and Parameters, select the right-hand side relay and click OK. Now I will complete the same process for the opposite side relay. Be sure to complete these steps in a timely manner to ensure the test is started before the 2-minute mark. Enter the same time as before in the test time box and click Initiate Test. Press Enter on the relay to initiate the test. If these steps have been completed correctly, you will now see both relays counting down in a synchronized manner. Now I would like to demonstrate the CFG Recorder Method. For this method, I need to combine all 6 signals into one bundle using breakouts and the control signal connector. This method requires the use of an add-on to the EMTP software. The tool is called a Comtrade Recorder. It generates Comtrade files as the simulation runs, and editing in ScopeView is not required. The next step is to configure the Comtrade Recorder. First, select the 2013 IEEE Comtrade format. Select the 32-bit precision option and set the stop time to 200 milliseconds, as well as the sampling frequency to 1 MHz. Now, I need to configure each channel. The names of the signals need to be provided, as well as the maximum and minimum values, which are chosen to best fit the test case. After entering the max and min values, the scaling factors are calculated automatically. Also, I select the secondary option for this case. Now, I check for errors. Then, I need to select the file location for the Comtrade file. I click the Select a CFG file name and choose a unique name in the same folder as earlier. It saves some time to copy the name before clicking Save. Next, click the Select.dat file name and paste the name from the clipboard and click Save. I'll leave the run number and auto increment blank, and I'm sure to uncheck the box that says Save Data File Names using Relative Path. Then click OK. Now, I need to connect the Comtrade Recorder to the signal bundle by clicking and dragging the mouse. I use the bundle connection window to carefully make the connections. Select the desired source at the top, then select the proper destination for that signal at the bottom. Then click Join. This must be repeated for all signals in the bundle, and be sure to click Join each time. After it is completed, check for errors and click OK. Instead of setting up another identical meter, it is much easier to just copy this one and paste it on the other end of the line. Open the settings to make sure things look correct. Next, I do need to select a new file name. Choose the same folder but designate it for the right-hand side. Keep all other settings the same and click OK. Repeat the same process for the connecting of the CFG recorder as before. Sometimes it automatically makes the connections, but always double check to make sure it is connected as desired. Finally, I need to configure the simulation settings like I did earlier in the ScopeView method. I set the step time to 1 microsecond and the simulation length to 200 milliseconds. I make sure the Save Intermediate Time Point box is unchecked and click OK. Now I'll run the simulation by pressing the green arrow above Run. When the simulation is complete, there will now be 4 new files in the folder, one .cfg and one .dat for each side. These files can be loaded on the relays with the same method used earlier in the demonstration. Thank you for watching this video on generating Comtrade files in EMTP and loading them on SEL-T400L relays. Okay, if there was any trouble viewing the video, I can make it available at any time. This presentation outlined 2 acceptable methods developed by the project team of generating Comtrade files for SEL-T400L playback testing. The ScopeView method is recommended for cases where only one sampling rate is required, or if users do not have access to the beta add-on blocks. The Comtrade recorder method is required for cases where line data and the EMTP relay model needs to be sampled at different rates. Using the Comtrade recorder block and the CFG files are automatically generated for each simulation. Comtrade files generated in EMTP can provide a very accurate representation of the transient response of a faulted power system, and these files can be used to test traveling wave-based protection schemes with confidence. I would like to give a special thanks to Mr. Jeremy Blair at SEL, who has spent countless hours of his time helping me learn this process. I would also like to thank Dr. Cox at Louisiana Tech for all the knowledge and encouragement he has provided me. I'd like to thank Henry and Mahalo at EMTP, who always provide technical support and suggestions in a timely manner, and Dr. Quinteros from Entergy for recommending me to present this topic and working with me along the way. Lastly, I would like to thank Mr. Field and Dr. Bhattarai for introducing me and for all the help completing this project. Thank you all for watching this presentation.
Thank you, Toby, and thank you everybody else who worked with you on this presentation. It was really impressive, and I'm sure that people have learned a lot from it. So now I invite. Yes, thank you, Toby. So I now invite everyone to type your questions in the questions menu of GoToWebinar, and we'll do our best to answer them. So let's start, Toby. One question asks, can this method you just described be easily applied to testing other SEL relays?
No, sir. There are only 2 SEL relays that have the capability, the T400L and the T401L.
Is there a workaround that could be adopted?
I'm not sure. I think this is basically a new technology, specific to traveling wave relays, and that really wasn't totally necessary before because they could be tested with other methods.
Okay, one question asks if the frequency transfer characteristics of PTs and CTs was considered in your model.
Yes, on our actual relay model that we are developing, we are indeed looking at the frequency response characteristic of instrument transformers. But for the scope of this presentation, we're just trying to focus on the how to get the Comtrade files generated in EMTP and get the relay to work with that. So that's why we didn't get into the details of the model. But yes, certainly we are definitely looking into the frequency characteristic of the instrument transformers.
Okay, thank you. And for the instrument, for their frequency characteristics, how did you get those?
So we are working with the manufacturers to do some tests for us. The relay manufacturers to provide some data, and we're also looking at some literature to develop high frequency model of the PTs and CTs. Again, this is we're definitely working on it, but it's not a fully completed the model yet, and we're also working on a paper. So we hope to get that sorted out within the next couple of months. But basically, we're relying on the manufacturers to do some tests to provide us that data.
Thank you. One question asks, what is the difference between testing the relay using SEL-T400L file and using double Omicron based on Comtrade files? Are you familiar with this?
Again, we might have misunderstood the question, but let me clarify what I understand. So is the question, what's the difference between the process that we're showing today and testing it with the double set? Is that the question?
Yes, yeah.
Okay, so the double sets and the Omicron test sets, what they do is they inject actual currents that the relay would see on the field. For example, I think it's called secondary injection test set. So they will be injecting certain amount of current and voltage into the relay, and the relay will make a decision based on that. And like we had discussed earlier, Louisiana Tech doesn't have those test sets. So therefore, and also generating traveling waves using those test sets it's a complicated, it's not as easy as generating, for regular phasor current. So therefore, that's why SEL had this new technology where the relay can be tested solely using the Comtrade generator method. So we don't even have the test sets. So if you have the SEL, these new traveling wave relays, you could actually do the entire process without even having the test set. That's the great advantage of having these two methods, is that you bypass the use of the test sets. Now, obviously, if you have the test set, you can still test it. We're not saying it's not necessary or something like that. It's just that you can actually do it without having those.
And the test set will not cover for the traveling wave the bandwidth that's required, not the current double sets.
Mm-hmm.
And you're limited by the number of traveling waves that can be generated with the test set. The Omicron can generate 2 traveling waves per phase, and the SEL test set only generates 1 traveling wave per phase. This method generates all of the traveling waves that you see in the event.
Mm-hmm. Thank you all for chiming in for this question. Okay, let me see if there's some more questions. Okay, so the last question I see is reads like this: SEL-T400L relay is used to a traveling wave. TWFL is used to locate a fault or to trip the line if TWFL is generated.
So we'll try to answer the best we can. Once again, we work at Louisiana Tech, and Mr. Field works at Entergy. So we don't want to answer on behalf of the SEL relay. All right, but the T400L relay can not only locate the fault, it can also make trip decisions, right? It's all capable of doing that. But what we're focusing on this project is developing the fault locator and the TW87 and other portions of the relay. So this relay is definitely more than just a fault locator. It has a bunch of different protection and tripping functions. And Mr. Field, would you like to add something to that?
It does both. There are different traveling wave trip functions that we have Louisiana Tech putting into the model, and it also has the fault location. We're preparing for a pilot installation, but the trip outputs will be disabled on the relay. We will only be monitoring during the pilot time, but we will be looking at how the relays would perform for both protection and distance to fault.
Thank you, Thomas. Thank you, Prashanna. So I think we have no further questions for your presentation. Therefore, thank you once again. It was really informative and really detailed, and we could tell that a lot of work and preparation has went into this presentation. So really appreciate it. Thank you for contributing to this year's EMTP user conference. I will now share my screen once again and give everyone a look at the rest of the agenda for stability and protection series.
Before we go, we'd like to also thank everyone as well as yourself for such a great technical support. You know, it would not have been possible without your help. So thanks a lot.
You're welcome. Thank you very much.
Thank everybody for watching.
Thank you. So as you can see on my screen, we have 2 more sessions coming up next week with 5 more presentations on Tuesday and Friday, September 29th, October 2nd. So Stability and Protection series resumes next week. In the meantime, there will be other presentations in Earth-based resources series and in switching transient series. Keep in mind once again that you can use the same link that you have used today to join the rest of the presentations of this same series. That's all from us for today. Thank you very much, and have a nice day, and see you at one of the upcoming presentations. Take care. Bye.